Hey Algebra 2 friends, today we're going to talk about infinite geometric series. So our video started off today with me basically taking somebody else's work and showing it to you. If you get a chance to watch this video, the YouTuber is Think Twice and it's called Infinite Sums Geometric Series Explained Visually. It may make more sense after our lesson and you can watch the entirety. I only watched part of it with you all. What I wanted to show you and what we'll talk about is the idea of adding infinitely many numbers in a geometric sequence, which is what we have here. So this geometric sequence kind of starts off with 1 or 1/2. Let's say it starts off with 1/2 and we keep multiplying by 1/2. So the R value is 1/2 as well. And so we're adding half of what's left every time. If we start off with half and then we add half of that and then half of what's left and then half of what's left, we'd have to keep doing this forever. And then our infinite series would get to 1. And so let's go back to our vocabulary and think about what an infinite series is. It's exactly what you think about it. Infinite geometric series is the sum of infinitely many numbers of a geometric sequence. So that's like the sum of all of them, okay? And it's kind of weird thinking about adding something that never ends. Keep adding, but it gives you a finite value like it did in those videos that we saw earlier. And so that's something we're going to toy with and talk about. And partial sum would be just the sum of some of the elements of a geometric sequence to form a geometric series, So the partial sum of a geometric series would just be the sum of some of the values. And we saw that in the last section where we had S sub n, which was the sum of all the values from a sub 1, or all the terms from a sub 1 to a sub n. And so with that, let's go ahead and take a look at another formula. So when we have an infinite series, an infinite geometric series, such that the R value is somewhere between -1 and 1. Sometimes this is written as R, the absolute value of R is less than 1, which really means the same thing. You can find the sum of the entire sequence by this formula. Looks so simple, right? So you can find the sum of the sequence. Well, let's think about R for a second. R has to be a number that is less than 1 or less than -1. And so what it means is each time we are adding a smaller value to our previous value. Because if I'm multiplying my a sub 1 by a fraction, that means I'm adding a fraction to it, either a negative fraction or a positive fraction. So keep that in mind as we are considering finding the sum of the geometric series. So in this case, if I wanted to find the sum of, let's say, that sequence that we saw where we had 1/2, and then the next one was 1/4, and the next one 1/8, as the R value is equal to 1/2. Let's go ahead and put it together. So what is the sum? The sum would be 1/2 over 1 minus 1/2. You guys see that? 1/2 over 1 minus 1/2. If 1/2 is the first term, let's see what we get. 1/2 over 1 minus 1/2 is 1/2, and you can see 1/2 over 1/2 is 1. If you so choose, you can say, well, it's equal to the 1/2 times the reciprocal, which is still 1. Okay, so we get 1. So we know that when we're adding this sequence, 1/2 plus 1/4 plus, we're adding this, finding the sum of the series rather, and we keep going in that direction, our answer is going to be 1. How amazing is that? Well, now all infinite series do not have a sum. All infinite geometric series do not have a sum. And you remember we just said that R has to be less than 1. The absolute value of R has to be less than 1. And so what we need to do is figure out if that's what we're working with as we move from term to term. What is our R factor and how do we find it? You remember we find it by taking the next term and dividing it by the previous term. So 3/8 divided by 1/2 is equal to 3/8 times 2/1 times the reciprocal. And with that we get 6/8, which can be reduced to 3/4. And your question is, so this is R. does R fit in this category? And since the answer to that is yes, then we do indeed have an infinite series sum, and so we need to find it. And to find it, we're going to use that formula. S is equal to, let's see, what was S equal to? I need to glance up here. S is equal to a sub 1 over 1 minus r. Let's make that a subtraction sign, please. 1 minus r, and so we are going to do it. A sub 1 in this case is 1/2 over 1 minus r being 3 over 4. And when I get 1/2 minus 3 over 4, that's 1/4. I'm going to take that. You see how we're rocking this thing, and I'm going to multiply by its reciprocal, and therefore I'm going to get 4 over 2, and therefore I get 2. When I add up all of these numbers, and I keep going with this pattern, multiplying each term by 3/4 to get the next term, I'm going to end up with the number 2. Checking on part B here, we're going to do the same thing. Remember, we need the absolute value of r to be less than 1. So let's check out what r is. How do I get from here to here? What am I multiplying? I'm going to take my -2 divided by 1, and what I get is -2. And so our value is equal to -2. And it makes sense because 2 times -2 gives me this -2 times -2 gives me 4, and 4 times a -2 gives me 8. So yeah, that's what r is, but r does not fit this criteria of being less than 1, and therefore there is no sum, there is no finite solution. So we write the sum does not exist. Okay, so let's check out an infinite series in sigma notation. This looks complicated, but I think we can figure it out. So we can see that if we start off with the number 1, this whole thing goes to 0. This is 0, and this therefore goes to 1. So our first term, our a sub 1 term, is clearly 24. Since we're dealing with this -1/5, you can see that r is equal to -1/5. And that gives me some information, and I want to know what the value is. And the best way to do this is to see, do we have the criteria where the absolute value of r is less than 1? And we do. Therefore, we can use our formula. And that formula is S is equal to a sub 1 over 1 minus r. So we'll make that nice and bold. All right, so dealing with this, let's go ahead and see what we can do. To find this sum, that's what we're looking for. We'll take the first term, which is 24, and we will divide it by 1 minus the r term, which is 1 over 5. Such a simple formula with a powerful job. So we get 24 divided by, this all becomes, if I look at this as 5 over 5, this becomes 6/5, and that's equal to 24 times the reciprocal 5 6. 6 goes into that, and we end up with 4 times 5, which is 20. So the sum of all of these infinite number of values will be 20. Pretty darn cool. Okay, so we've come to our final example, and I'm going to do this one way. I don't know if if you don't like it, the text might do it another way. If I have time, I'll do it both ways, but we'll see. So we're going to write this as a fraction. Anytime you have a repeating decimal to write as a fraction, there's kind of a neat way that you can do that. And so here's what you do. You first start off by saying, okay, let n, the number, equal 0.039 repeating, and you get what's going to happen there. And then what you're going to do is you're going to multiply both sides of this equation so that the repeating part is in front of the decimal. So the part that repeats is 3939, and so in order to get that 39 in the front, I'm going to have to multiply by 100. So what I do to one side, I do to the other. So when I multiply n by 100, that's really making this number 39.3939 repeating, okay? So that's key. At this point, what we're going to do, since this is equal to this and this is equal to this, we're going to actually subtract 100n by n. So on the right side, I'm going to say, well, that's 100n minus n. And on the, well, this is the left side. On the left side, I'm going to say that's 100n minus n. And on the right side, I'm going to say, well, since 100n is 39.39 repeating, I'm going to subtract from that 0.39, which is n. You guys follow me? This is equal and true. So what I get on the left side is 99n, and what I get on the right side is just the number 39, because I've gotten rid of all the repeating parts. And so now I'm going to divide both sides by 99, and we have the fractional version of this answer, 39 99ths. Can I reduce this? Of course I can. I can divide top and bottom by 3, and so I get 13/33, and I think that's the best I can do. So 13/33 is the value of n. A final look at this problem reveals a series here, basically a geometric series. Let's take a look. So if we look at the 39s, let's try that again. If we look at the 39, 0.39, it's really 39 hundredths. That's like this group. And then plus 39 thousandths and plus 39 hundred thousandths. And we can keep going on and on. And so if we look at this, we do have a geometric infinite series that can have a value. And again, we're going to pull out our equation. S sub S, not S sub anything, is equal to a sub 1 over 1 minus r. I'm telling you, the equation is so simple, but I really am struggling to remember it. So you know. So a sub 1 over 1 minus r. And so in this case, a sub 1 is 39 over 100 divided by 1 minus r. So what is r? What am I multiplying to get from one term to the next? If you look, you can see that r is equal to 1/100th. So if I multiply the denominator by 100, that's all that's happening, but the top stays the same. So I've got 1 over 100 like that. But 1 minus 1 over 100, my bad, almost messed that up pretty badly. So I get 39 over 100. And so if I look at this as 100 over 100, this would be 99 over 100. And so 39 over 100 times 100 over 99, you see where this is going, we get 39 over 99, which we saw reduces to 13/33. All right, I think my son wants me to stop chatting because he wants to be chatting with me. So I'm going to let you guys go, and that is the last example. If you have any questions or concerns, please let me know, and I look forward to talking to you all soon. Take care, guys. Bye-bye.